All right, turning points are places where a function switches from increasing to decreasing or from decreasing to increasing. Okay, these points are called local maxima and local minima. These are just the plural forms of maximum and minimum. Okay, so, and that makes sense. I'm going up, and then I'm going down, then I'm going up. So wherever it switches, okay, like a roller coaster, wherever I'm switching from going up and down, okay, those are my turning points. And I have this local maximum and local minimum. And why are they local? Because they're in a certain place. Okay, because obviously there is no maximum to this function, there is no minimum to this function, and so that's why we look at the ones that are within a certain range. Okay, so turning points of polynomial functions. The graph of every polynomial function of degree n has at most n minus 1 turning points. Okay? Then, as a kind of a second part, if a polynomial function of degree n has n distinct real zeros, that means that's where it crosses the x-axis, then its graph has exactly n minus 1 turning points. So for example, I could have a polynomial x, say x to the third. Remember, we've done this before, and it kind of goes like that. Okay, so, well, maybe I shouldn't do x to the third. But there are some that look like this. And there really are no turning points. Okay, so for number 1, it says it has at most n minus 1 turning points. So this is a function, say x to the third power, and there's no turning points. However, if I have x to the third, or let's do x to the fifth. No, x to the third. Okay, something with x to the third, and it goes like this. I have 3 real solutions, 3 real zeros, okay? And I have 1, 2 turning points. So if I have a function with 3 real roots, it crosses the x-axis 3 times, I can only have 2 turning points, and that makes sense. This is really just a complicated way of looking at this. If I have a y to the fourth, I'm sorry, x to the fourth, okay, and it goes like this, crosses 4 times, and it has 1, 2, 3 turning points. Now, that's not exactly what x to the fourth looks like. X to the fourth looks like a parabola, but if we have a function that is a 4th degree, it could look like this. Okay, I hope that made sense. All right, so finding our turning points. If you read the book, it's a little confusing because the book tells you to use a graphing calculator, and I know that most of you don't have one. So we're doing the best we can with what we've got. Okay, so this says graph each function, and I've graphed it already. Identify the x-intercepts and the points where the local maximums and local minimums occur. So let's do that first. So right here are my x-intercepts. So I have an x-intercept at -2, 1, and 3. Okay, also it says, determine, where these maximum and minimum are. This isn't exact. You can see that it's kind of a little bit to the right of this line right here, but I'm just going to say that that's a really big dot, and just say that it crosses, okay, it maxes out at -1. So my maximum is -1, 5, 6, 7, 8. And my local minimum is approximately 2, -4. So my maximum is roughly negative 1/8. My minimum is roughly 2, negative 4. Again, it's not exact, but without a graphing calculator, that's about as good as we can do. Okay, now determine the intervals for which each function is increasing or decreasing. We've done this before, okay? So we know that we're increasing from negative infinity, okay, to this point right here, but we look to see where we're at on the x-axis. Okay, so we come to about right here. Okay, so it's increasing until we hit this point, which is right here. So that is negative 1. It's also increasing from this point right here to infinity. So this is the point 2 to infinity. So it's got to be decreasing between those. So we're going from negative 1 to 2 is where it is decreasing. Okay, hopefully that you remember that from before. All right, the rest of this is the stuff that we're not doing. Here's your homework. It is in Big Ideas. Let me know if you have any questions.